Hey, my name is Eric and welcome to DataFool. I present awesome data science cases from some of the best data scientists and machine learning engineers in the world. Today I have a real banger for you and we learn how to make XGBoost classification more than 100 times faster. I'm super excited and you would be foolish to miss this case, so let's get started. If you missed my earlier video on these topics, the notebook today is one of the highly rated notebooks in the recent American Express Kaggle competition that ran from May and August earlier this year. American Express is one of the largest payment providers in the world, and they launched this competition to develop an algorithm to predict if a customer will not be able to make a payment on a future credit card statement, given the customer's credit history. One very interesting aspect about this competition is the enormous size of the data, which is more than 50 gigabytes. Just the training dataset alone is 16 gigabytes, and then the test dataset is another 33 gigabytes. Amex provides us 188 features across all the customers, which we can use to build our model. And this is where the graphic cards comes in really, really handy. Because the graphic cards, you can think of it as essentially a highly parallelized version of your CPU. So when you have massive amounts of data that requires to do the same operation over and over, this allows us to actually use parallelization, giving us this huge speed improvement potentially by using the GPU. And then I want to give a shout out to Chris, who actually is the author of this notebook. Really, really appreciate him contributing to the community. He's one of the most prolific data scientists on Kaggle. You can see he's a quadruple grandmaster and the #1 grandmaster for notebooks and discussions on Kaggle. The case we're going to discuss today is called XGBoost Starter. And as always, you will find a link to the notebook in the comment section. First, I want to talk about the import section. Besides the usual suspects, pandas, numpy, and matplotlib, you notice this cupy and cudf libraries that are being imported here. Cupy is thereby an implementation of numpy and scipy, but using the graphics cards processing units. And you might have guessed it, cudf is an implementation of pandas, also using the graphics cards processing unit. In fact, most of the magic and the speed improvement will live in these two packages. You can go to the cupy page, for example, and there they have a direct comparison between the speedup of cupy and numpy. For large data sets, you can see that the speedup can actually exceed a factor 200 for certain types of operations. And in fact, we will see that the improvement we see today with XGBoost is on a very similar scale. Cupy and cudf have thereby been implemented to almost mimic pandas and numpy one-to-one. So in many cases, you can simply swap out the cupy command for the numpy one and the cudf command for the pandas one, and the code will look exactly the same. So the first thing we're going to do after importing our packages is we want to import our training data, then we want to import our target data, and then we want to do some basic feature engineering before we can actually call the XGBoost function. So let's talk about importing our training data. Chris wrote a nice function here to import our training data. And on a first look, this looks very similar to how it would look like if you wrote this with pandas. However, you will notice that the data frames that get initialized use actually the cudf function. The readParquet function is something you will find in pandas. The fillNaN function looks exactly the same in pandas. So everything looks the same. However, instead of PD, we use cudf. And what is the difference? Well, cudf will, if it can, utilize the GPU to speed up some of this pre-processing. So let me actually execute this code, and then we can just look what this Kaggle notebook is doing here. And we should see after time, not only the CPU usage RAM going up, but also the GPU. And in fact, you can see this just jumped to 600 megabytes, indicating that the GPU is in fact being utilized here. So Chris does actually not utilize the original 16 gigabyte CSV file, but instead we're using a dataset provided by a Kaggle user called Radar. The original Amex competition had put artificial noise into the dataset to obfuscate the values. And this is actually one of the reasons the dataset blew up so much and has this large file size. We talked about this extensively in the first video. And some really clever users around Radar have actually realized that you can reverse that process and you can remove this noise and do some typecasting. And this will, first of all, remove noise, which is obviously great from a machine learning perspective, but it will also shrink the data size tremendously. So Radar provided then this denoise data set as a Parquet file, which is a binary file format. And instead of a 16 gigabyte file, we now have to work with an only 1.6 gigabyte file. So what's Chris doing here? He imports this readParquet file using cudf, and then does some very basic transformations on some of the columns. The customer ID column was a unique hashed ID of every customer identifying it. He just truncates it and turns this hex value into an integer, so it can be better processed on the graphics card. He also turns the only datetime column in the dataset, which was column S2, into a regular datetime as you would with a pandas data frame. And that's pretty much it. And then he returns everything and outputs this as a train variable. If you use actually type train, you will notice that this is not a pandas data frame now, but actually a cudf. It's a cudf core data frame. Here we can have a quick look at this train data set. As I was saying, there is a unique customer ID associated with every customer. There is the statement date column, the S2 column here, and then there's a range of features, most of them being numerical. As we also mentioned in the first video, we don't know what any of these features mean. We're not given any categories, we're not giving any descriptions, and there's also no human readable information actually. Everything has been obfuscated. We do know, however, that there is about 11 categorical features, and then the remaining ones are all numerical ones. So all of our transformations will be split essentially into two parts. So let's talk about the process and feature engineering section. This is probably one of the shortest feature engineering section you will find in a data science challenge. And the reason is twofold. Keep in mind, this is a starter notebook, so this is just meant to give you an idea how to solve this Kaggle competition. And second of all, we have a lot of features, 188 across 500,000 users. The data remains relatively massive. And if you want to make transformation on each of these feature columns, the data will just blow up quite a bit. So for this feature engineering, we're going to split all the features into two types, categoricals and numericals. The categoricals are shown here, and then the numericals you can just calculate by taking all the features minus the categoricals. And what we're going to do is we're going to take the numerical features and we're going to calculate for the 13 or so statements we receive for a customer, the mean for every numerical value, the standard deviation, the min, the max, and then the last value associated with every numerical feature. The output of this is 1 row per customer, and you will receive roughly 5 feature-engineered features per numerical feature. Very similar for the categoricals, we're going to aggregate per customer ID, and we're going to take the count of categories per categorical feature, the last category found for each user, and also the number of unique categories per user. This is, again, 1 customer per row, and we concatenate both of this into one feature-engineered training data set, which will then be returned. I've also included this df fill nan here, which just fills all of our nan values with the default value. So let's talk about the last section of the data preprocessing part. Here we want to import the target column. We're going to use for that the original data coming from the Amex competition called trainlabels.csv, and it contains 1 row per user and just simply a yes or no if this user has churned. This is what we want to train our machine learning model on. You will notice that we're going to use, again, cudf because we want to join this target data with our train data set into one large data frame. So in terms of processing step, Chris is just changing, again, the customer ID to a numerical value. He then sets the index on the customer ID, and then he merged this target column on the train data set itself. There's one very interesting note, however, he makes. He starts sorting at the end the train data set by index, and makes the note that cudf, the merge is above randomly shuffled. So there are actually differences between pandas and cudf, and this is one of them you should be aware of. Sometimes there's funky things happening when you use the graphics card. And in this particular case, when you merge two data frames, the order of the rows might be changed. So as a workaround, you can just always sort your data frame afterwards to maintain the same order you can expect. The output data frame train now contains all aggregated features plus the target column. We're also saving the names of all the feature column in a list variable called features, as you can see here. And this is what we will ultimately use for our machine learning. Let's talk about setting up XGBoost. You will notice that we import XGBoost here as XGB, and we're also checking for the version, which is something I highly recommend you doing. XGBoost is still in active development, and they're constantly changing things, and something that might have worked on a version you've used in the past might not work on a version that works in the future, and you're going to get some kind of obscure error message. So I definitely recommend keeping track of your version you have actually installed. Chris then initializes all these hyperparameters for the XGBoost classifier, and the most important ones are actually coming towards the end. If you want to use the GPU instead of your CPU, and see this big speed improvement I have promised you, all you really have to do is to change these two values. By the way, for reference, I also included all the default values that usually come with XGBoost, so you have a nice little side-by-side comparison. So the predictor variable you want to set to GPU predictor. It's typically set to auto, which means it's trying to use the GPU if it's available, but otherwise it's just using the CPU. On the tree method, you want to pick GPU hist. While hist would be the one you would use on the CPU, but it's also typically set to auto. And last but not least, the most important parameter you want to set is also this objective function. In this case, we're going to use binary logistic regression. I haven't talked much about logistic regression before. You can read up on it in any decent machine learning book, and I will also post a link to a Kaggle tutorial of why binary logistic regression is what we want to use for this specific case. It's a binary classifier. Binary logistic regression is a very common method to use for binary classification. So let's talk about the other hyperparameters. We have eval metric, call sample by tree, subsample, learning rate, and max depth. Eval metric is something that's at XGBoost very closely tied to the objective function you pick. For binary logistic regression, the default evaluation metric is log loss. So you typically just want to leave it as it is. We're just explicitly mentioning it here so it's clear. And call sample, subsample, and max depth are three hyperparameters you typically want to tune to prevent overfitting. If you look at these default values, you can see that Chris actually picked values that are slightly lower than the default values. Subsample just means that for every tree, we're going to subsample a certain amount of our training data, in this case, 80%. Call sample by tree means we're going to subsample a certain amount of features also by tree, in this case, 0.6%. And max steps just means how deep can these trees actually be. This is a value that goes from 0 to infinity. Typically, you want to set it like to something around 6, and Chris chose something even slightly smaller. And then the learning rate just means by how quickly we want the model to evolve. And we can tweak that a little bit depending on later how we see how quickly it converges or not. I'll talk about this in just a little bit. And you might be wondering what this random state also stands for. Well, you might have guessed it. We do some subsampling here, so there is some randomness in the system. If you want to fix this randomness, as you would with any other situation where you use random number generator, you can fix essentially this randomness using a seed right here. If subsample and call sample were set to 1, this random state parameter had no influence whatsoever. So this is all you really need. All you really need to focus on are these three variables if you want these two GPUs. So let's keep talking about the next sections. So Chris then provides this function called iterload matrix, and he actually provided very little information on where this is coming from. You can then go actually to the discussion section of the notebook, and he explains to you that this is a custom function he wrote to make the code even more memory efficient. And this brings us already to the last and most important section of this data case, where we're actually going to train XGBoost with the graphics card. So this section looks rather convoluted and complex, but all the magic happens in a few lines of code. And most of the other things are only initializing variables, printing out statements, and doing a bunch of bookkeeping. So let me then quickly show you what the section looks like. The first part is initializing cross-validation via k-fold. The middle part is preparing the data for XGBoost, then calling XGBoost with our data and the hyperparameters we have defined above. And then it's just executing the model on our validation set and saving the data in respective variables, so we have all of them available after the model training is completed. So let's jump back to the top. Chris decided for a 5 k-fold cross-validation. If you've never heard about cross-validation or k-fold, what is the basic idea here? We slice our data into 5 pieces. We take the first 4 pieces for training it, and then the 5th piece for validating the model. Then we change for every fold. So for every iteration, we're going to change the 4 pieces we're going to train on, and we're also going to change the 5th piece we validate on. Because there's 5 folds, you're going to get effectively 5 models to be trained, 5 accuracy values over which you can average and can calculate a standard deviation to get a better sense how well your model generalizes. So let's talk about this intersection. You can think about this section as the data gymnastics, where you want to convert the data into a format that XGBoost likes to ingest. And in fact, XGBoost likes to ingest its data in this D matrix format. So in the first step in our training data set, we're going to use this iterload for matrix function that Chris defined and going to give it our training data with the training indices for this fold. We're also going to specify the feature columns as a feature list and the target column name as a target. We then call XGB device quantile matrix and give it this XY train object we've just created. What is device quantile D matrix? So device quantile matrix is a more optimized version of D matrix. And Chris prepares the data for device quantile matrix using the interload for D matrix. Why does he do that? Is that needed? The short answer is no. You could absolutely use just the XGB D matrix function and give it the train data and the test data for the specific fold, and the code would just work fine. However, you're going to see about a 30% speed improvement by using this device quantile matrix on the training data ahead of time. This device quantile matrix, in fact, pre-calculates quantiles of your data, which is then handed over to the GPU hist function, reducing the memory and processing consumption of the GPU. So all Chris does here is really, he does a little shortcut. He pre-computes the quantile in the data using this function. And that actually saves us a little bit more time. In a realistic setting, you might want to skip this section and just implement everything with the D matrix. We're then going to also define our X validation and our Y validation data portions by slicing out the training data on the validation indices, giving it the feature columns, and for Y validation, we're slicing it out on the validation indices using the target column. Both of these are now being passed into XGB D matrix again to construct a D matrix for XGBoost. At the end, we end up with two D matrices, the D train and the D valid. And this is really all we need for XGBoost to work. Okay, so now we've prepared our data. We have defined our XGBoost parameters above in the data dictionary. And we're going to feed everything to the XGBoost train function. XGB parameters are just given as a dictionary. Dtrain is being handed over as dtrain. And that's technically all you need to run your model. All of these other variables are optional again. However, XGBoost runs per default with 10 boosting iterations. And it doesn't matter if your model is underfitted then or overfitted, it will stop after 10 iterations and it will give you the model that you have after 10 iterations. This is not always the best approach. A better approach is to use early stopping rounds. What does that mean? Early stopping rounds just means that your model will try to improve the accuracy at every early stopping iteration, but if it doesn't see any improvement anymore, it will stop early. And it will only go to a max number of early stopping rounds itself. This is a much better approach because if your accuracy already converges, you can finish the model much earlier and you can be guaranteed you're finishing actually at the highest accuracy. This also will prevent overfitting because the model will stop itself the moment the accuracy score does not see improvement any further. To use early stopping, you have to define this evals function, which looks a little funky. It's kind of like this list type thing of two tuples, but really you're only handing it the dtrain data object and the dvalid data object, and you just tell them the evals function that this is actually your train data and this is your validation data. So what does this look in real life? Let's execute this. You can see that we're starting with fold number 1. It's using 4/5 of the data, or 367,000 data points for training and 91,000 as validation. And then for each boosting iteration, it will actually output the log loss for both the training portion of our data and the validation of our data. And as you can see, the log loss is actually decreasing, which is what you want. The log you usually want to see decrease. You can also see that it actually converges. What that means is you will see bigger jumps in the beginning, and then the jumps actually of improvement will get smaller and smaller and smaller. And this is exactly where this early stopping will kick in. As soon as these improvements decrease by a certain amount, do not decrease by a certain amount anymore, the model will stop and will move on to the next fold. How can you actually define what the early stopping criteria is? Well, it either stops after 100 iterations, or you can set it through the learning rate. By picking a larger learning rate, it will have fewer boosting iterations. If having a smaller iterations, you will see that it will converge slower. So all you really need, just to repeat one more time, you need to define your hyperparameters and you want to hand it the dtrain one. I recommend using early stopping. That usually can already give you a nice boost in your model by defining the early stopping rounds parameter. Just set it to some high number and then also defining this evals. I'm actually not 100% sure if you do need to set the num boost round if you define early stopping, but Chris sets it here to some arbitrary high number that we will never reach. So while the model keeps training, I can explain the rest of this section. So while the training part is really just this one line of code after initializing of the data and the parameters, we will then save the model to a file by also denoting the fold we have been using. It saves it in this XGB file format. There is equivalent to save model and load model functions, so you can later load your model again and apply to some data without having to go through the whole training process. In the next step, we want to save the feature importances. We're going to use a model.getScore function for that. And that returns a dictionary, and we want to return this into a data frame as follows. We then attach this data frame to the importances list. Keep in mind, we're training 5 models, 1 for each fold, so we're going to get 5 importances data frames. You can then later concatenate those, take the average over those to get some overall importances for the whole 5 models, whatever you like. But for now, we're going to be left with 5 importance data frames. We then want to infer what the model is actually predicting for our validation set in this specific fold. We're going to use model.predict. Chris names this OOF predicts, where OOF stands for out of fold prediction. Typically, this is called like Y_prediction or Y validation prediction, something like that. The output of that is what we want to compare to the source of truth, which is our Y valid dataset itself. And we're going to use the AMIC metrics accuracy function. Typically, this would be also like a scikit accuracy function, but in this case, the competition comes with its own accuracy modality. So feeding in the Y validation values, feeding in the predicted values for that validation step gives us the accuracy for that fold. And we can print that out. How does that look like? If you look down here, you can see that for every fold, we now get a Kaggle metric, which is on the order of 0.79. Very similar to the importances data set, we also want to then save the information from every fold into a data frame. So the OOF list contains 5 data frames with the out of fold prediction for every fold. At the end, we're going to concatenate all of those into one large vector. So we're going to get 1 result per customer per row with 1 value with a probability predicted. And then the last part in this for loop is actually cleaning up memory. And that's something that's always highly, highly recommended for large data sets like this, because it's very easy to run out of memory in these notebooks. So you can see we're deleting actually dtrain, dd, df, xvalid, yvalid, dvalid, and model. All of those are being reinitialized in the next iteration. This gc collect is just a generalized garbage collection. At the end, after all 5 folds have been trained, we're going to save the results of the out of fold prediction, which is 5 data frames again, into one large data frame. Once we've concatenated all the out of folds into one long column vector, we can now actually calculate an accuracy score for the whole data set. So we're going to use again the MX metric function. We're going to feed it all of the out of fold values, which is 1 customer per row with a target value, and also the predicted values. And we're just going to get an overall accuracy. Similarly, you could just take the average over all of these 5 data frames you got, could also apply the standard deviation, and you would get a range of prediction values if that's something what you prefer. So at the very, very end, once the model training is finished, you're also going to get your overall accuracy, which is obviously some sort of average over each of the individual accuracies. So this is it. This is all you need to do to train XGBoost on your graphics card. So because this was a lot, let me just go through it one more time from the beginning and quickly say what's really important. First, you want to import QPy and QDF in the import section. Then for your data preprocessing, you want to start using cudf to munch the data. Is this strictly required for running XGBoost on the graphic card? Absolutely not. You can absolutely use pandas here. XGBoost at the end actually takes it as these D matrices anyways. It doesn't care if it's a pandas data frame or QDF data frame. However, you will already see significant boost up in the data processing by just using the QDF library instead of the pandas library. You then want to go to your hyperparameters and set the predictor method to GPU predictor and the tree method to GPU hist. You probably also want to set things like max step, subsample, or column subsample to prevent overfitting. And last but not least, you want to reformat your data into this D matrix that XGBoost likes to ingest. You can follow that what Chris does here, or you just use the D matrix approach from the XGBoost library. Once you have your train data and your validation data in this dtrain dataset and this devalidation dataset, you have all you need to call the model. You call the model with the XGBoost parameters, then you feed it the dtrain. You call the evals by giving it the dtrain and the devalids, just so you get log laws at every step, and you set the early stopping rounds. That's all you really need to call XGBoost on the graphics card. So in this spreadsheet, I've summarized for you the actual improvement times you can expect with a GPU. I ran all of this on kfold equals 3 because it runs really, really long on the CPU, and I couldn't run it any longer in the Kaggle notebooks itself. The four modalities I'm comparing here is CPU plus D matrix. This is probably what you would run per default if you didn't use the GPU. Then CPU plus device quantile matrix, GPU plus D matrix, and then GPU plus device quantile matrix. And I've ranked it here by performance. So let's start with the slowest, which is the CPU plus the D matrix. This ran for almost 8 hours. Just by switching from the CPU to the GPU, we're already getting a 95 times improvement, and it went from 8 hours to about 5 minutes. By then using the device quantile D matrix instead of the D matrix itself, you can expect another 30% improvement. So in total, from the slowest to the fastest, we see a 120x times improvement in execution time. And this is really where the GPU shines so much. It makes a problem with a lot of data from being intractable to actually tractable. So big shout out again for Chris for sharing this with the community. I thought this was a super awesome case. I already learned a ton, and I also started implementing this in some of my data science cases at work. My name is Eric, and this was our case for DataFool. If you like this case as much as I did, definitely push the like button and give me some feedback in the comment section. Until next time.